Okay, so let's do a quick recap on the two types of improper integrals, and then we'll have a look at some examples. So the first type is if we have some sort of infinite domain. In other words, we've got a picture like this, okay, where your function might do something like that. Okay, and it asymptotically approaches the x-axis, for example. And what we want to find, let's say from here, okay, from A going to infinity, we want to find this area. Okay, so that area in blue going all the way to infinity. So we start off by writing the integral from A to infinity f of x dx, but we can't just substitute infinity as an upper bound. It's not a number. You can't just plug it in as if the upper bound were something like 2. Instead, we replace infinity with another variable, usually t, and then we take the limit as t goes to infinity. So instead of writing this, we write the limit as t goes to infinity, and then the limit from a to t, f of x dx. So this way, we can calculate the integral. We know how to do that. It's just a definite integral with a lower bound a, upper bound t. We can do that. And then we've got the limit, which we also know how to do. Okay, so instead of having the problem of infinity in the upper bound, we replace that with this idea of a limit as t goes to infinity. Okay, because then we can handle this. Yeah, there we go. Cool, thanks for that. Okay, so instead of having this upper bound of infinity, we replace that with a limit. Now, if the lower bound was something like minus infinity, we would do the same thing. So if we have the integral from minus infinity to a, f of x dx, that's going to be the limit as t goes to minus infinity now. Then we're going to have the integral from t to a, f of x dx. And again, the definite integral, that's easy to do. It's just an upper bound a, lower bound t, no problem with that. And then after that, we're going to get some function of t, and then we take the limit. Okay, and then after we take the limit, that's our final answer. If the limit goes off to infinity, then we say the integral diverges. So if t goes off to infinity, or t goes to minus infinity. Yep. So either of these cases, and the limit goes to infinity or minus infinity. Then we say it diverges. Okay, so if your limit goes off to infinity when t goes to infinity, then the integral diverges. If t goes to infinity, or if we're saying t goes to minus infinity, and the limit stays finite, then we say the integral converges. Okay, and it converges to whatever your limit value is. Okay, so these are the two cases that we can deal with. You either have a diverging integral or a converging integral. Okay, but in both cases, the integral is improper because either the upper bound is infinity or the lower bound is infinity, or maybe both are infinity. Okay, any of those cases, we say that it's improper. And so we need to replace it with this idea of the limits first over here in red, and then we have the integral in green there. Okay, so that's the first kind of improper integral. The second kind is if we have some sort of discontinuity in the interval. So second type of improper integral. Okay, so for the second type, you can think of the following picture. Okay, so we've got our interval a to b, and let's say there is a discontinuity at a. Maybe the function goes off to infinity, like that. Okay, but then it remains finite going up to b. Okay, but here we've got ourselves a vertical asymptote. Okay, so we've got this problem at A. Okay, there's this asymptote at A, but maybe the area is still finite if we take the limit. Okay, so what we do in this case, we can't substitute A because the function is infinite. Okay, you can't just substitute A into your integral. So instead, what we do is we take the limit approaching A. Okay, so we can't do it directly, so we take the limits instead. So here, the integral from a to b, f of x dx. Okay, we know there's a problem at a, the function goes to infinity. So we say this is the limit as t approaches a plus, because we're coming from the right-hand side. So we're going this way towards a, so it's from the positive side. And then we have the integral from t to b f of x dx. Okay, so t can start off, say, somewhere here. That's t. And then what we're doing is we're taking the limit as t goes to a. So as this point here goes closer and closer to this asymptote, we want to see, does the area remain finite or does it go off to infinity? Yeah, again, if it remains finite, we say that it converges. If it goes to infinity, then it diverges. Okay, and similarly, we can do the same thing if B has an asymptote. Okay, and then what happens if the asymptote is in the middle of our domain? Okay, so it's not too much more difficult. So let's say we have x here, a to b, and at some point c in between here, the function goes off to infinity like that. Okay, so maybe it looks something like this. Okay, we still want to see, would this area remain finite even with this asymptote? Okay, so we got this area, we've got this asymptote here, so we need to take care of that. And it's somewhere in between A and B. Okay, so in this case, we need to take two limits. We need to look at the area on the left-hand side and take the limit going to C. We also need to look at the area on the right-hand side of the asymptote with the limit going to C. So in this case, the integral from A to B, f of x dx. Okay, we know there's a problem at C, so this is going to be the limit as t goes to C minus, because we're coming in from the negative side. Okay, integral from A to t, f of x dx. So again, we can't just substitute C directly because it's an asymptote. Okay, so that is the left-hand side. We also need to add the right-hand side. So that will be the limit as t approaches C plus, because now we're coming in from the positive side. And this will be the integral from t to b f of x dx. Okay, so we got these two sides. So let's say the green side over here and the yellow side on the other one. So the first integral will calculate for the green side, and the second integral will be for the yellow side. And if we add it together, that's going to be the complete picture. Now, if either of these diverge, then the integral diverges. So for this to converge, we need the green to be finite and the yellow to be finite. So to converge, we need the green part and the yellow part to converge. Okay, so if one of the parts goes to infinity, then we say that the total integral diverges. Okay, so let's take a look at some examples. Okay. Example number 1, we have the integral from 1 to infinity, 1 over root x dx. Okay, now we see that the upper bound is infinity, so it's an improper integral. So we need to make this proper by replacing that infinity with a limit. So this will be the limit as t goes to infinity, integral from 1 to t. We can do that, no problem. And then we have x to the minus 1/2 dx. Okay, so now we can leave the limit alone for now. We're focusing on the integral. So we add 1 to the exponent to make it a half, divide by that, that's going to be 2. So it will be 2x to the half from 1 to t. Again, we're not looking at the limit, we're just focusing on the integral. So this will be the limit as t goes to infinity. We substitute t, and we substitute 1. Yeah, so it'll be 1 times 2. So this will be the limit as t goes to infinity of 2t to the 1/2 minus 2. Okay, so integral's done. We've substituted, we've simplified. Now we take the limit. Now the limit as t goes to infinity of root t, that's going to be infinity. Because if you just remember the picture, it looks like that. This goes all the way off to infinity. Okay, so it's not bounded by anything. So this goes to infinity, which means our limit goes to infinity. And so the original integral also goes to infinity. And since it goes to infinity, we say that the integral diverges. Okay, so there's no number that we can put down for this integral. Okay, I've got a question here. Please repeat the second step. Which second step? Taking the limit. Which second step are you referring to? Taking the limit. Okay. So here, when we're taking the limit, remember your limit laws from last year. We're taking the limit as t goes to infinity of 2 root t minus 2. Okay, so over here, this is going to be 2 times the root limit as t goes to infinity of t minus 2, because the limit of 2 is just 2. Okay, it doesn't change. So we're taking 2 root infinity minus 2, but this is just going to be infinity, right? If you take the square root of infinity, you're going to get infinity. So that means the limit goes to infinity, and so the integral also goes to infinity. Yeah, so we say that it diverges. Okay, let's have a look at another problem. Okay, so we have the integral from, let's say, -2 to 3, 1 over x plus 1 dx. Okay, so now from -2 to 3, is there any point at which this function becomes discontinuous, or does it go to infinity? Yes, because when x is equal to -1, the denominator becomes 0. Yeah, and we can't divide by 0. So we've got a problem at -1. Okay, so what we need to do is separate this out because we know that -1 is going to be an asymptote. So this is going to be the integral from -2 to -1, 1 over x plus 1 dx, plus the integral from -1 to 3, 1 over x plus 1 dx. Okay, so I split it up because I know that this -1 here is going to give us problems because that's a vertical asymptote. Okay, so we know that it's improper, right? Because the bounds are going to be infinite. Okay, at -1, it goes to infinity for the first integral. At -1 for the second integral, the function also goes to infinity. So we need to replace those bounds with limits. So this is going to be the limit as t approaches -1 from the minus side. Okay, integral from -2 to t, 1 over x plus 1 dx, plus limit as t approaches -1 plus integral from t to 3, 1 over x plus 1 dx. Okay, so now we've got these two integrals to calculate. So let's call the first one 1, we call the second one 2. Okay, so if we try and do number 1, we're going to get the limit as t approaches -1 from the negative side. Integral from -2 to t, 1 over x plus 1 dx. Okay, so this is going to be the limit as t goes to -1 minus the integral of 1 over x plus 1, that's going to be the natural log of x plus 1. And we're going from -2 to t. Okay, so again, I'm not even looking at the limits. We're just working on the integral. So that's going to be the limit as t approaches -1 from the minus side. If I substitute t, I'm going to get the natural log of t plus 1 minus the natural log absolute value -2 plus 1. Okay, so that's going to be the limit as t approaches -1, natural log of t plus 1, and -2 plus 1, that's going to be -2. We take the absolute value, so we get 1. The natural log of 1 is 0, so this is just going to be 0. Okay, so now we're taking the limit as t approaches -1 from the minus side, the natural log of t plus 1. Okay, now if t is going to -1, then this inside part is going to go to 0. So as t goes to -1, this inside part goes to 0. Okay, and we know from our natural log that the natural log of 0 goes down to -infinity. So if you just want to keep the picture in mind, natural log of t looks something like this. And this is going to go down to -infinity. Okay, when t goes to 0. So that means this limit goes to minus infinity. Okay, and so it diverges. Okay, so we know that the first part diverges. Okay, and remember what we said, we need both parts to converge for the total integral to converge. Since the first part diverges, the whole thing is going to diverge. Okay, any questions on that? I've got a question here. Which part was affected by the absolute value between 2 and 1? Because I thought it was going to be 3. So you're just taking the absolute value here. So remember, the integral 1 over x plus 1 is equal to the natural log absolute value of x plus 1. So here, when we're substituting minus 2, this bit over here, we're taking the natural log of the absolute value of minus 2 plus 1. Minus 2 plus 1 is minus 1. So it's the natural log absolute value minus 1. The absolute value of minus 1 is just 1. And the natural log of 1 is 0. Okay. So remember your absolute values with your logs here. Okay, so whatever's inside, if it's positive or negative, you always take the positive. Okay, same goes for this first one. Okay, whatever's inside, you always take the positive of it. Okay. Any other questions before we move on? Okay, let's take a look at another example with the comparison theorem. Okay, so let's say I wanted to do the integral from 1 to infinity of 1 over x squared plus x dx, something like this. Now, if this was 1 over x squared, this would be pretty easy to do. Okay, but instead we've got 1 over x squared plus 1. So we make a note to ourselves. If the denominator was x squared, then this would be easier to do. Okay, so that's the idea in mind. We want to try to get this denominator to be x squared rather than x squared plus x. And the way we do that is we use inequalities. So we use inequalities to create simpler function bounds for the given function. Okay, so we're given this complicated function 1 over x squared plus x. What we do is we use some kind of inequality to make this either greater than some simpler looking function or less than some simpler looking function. Okay, now we know 1 over x squared, we know that that converges because it's got a p-value greater than 1. So in this case, we expect this to converge. So we need to prove that it converges. So we're going to use the comparison theorem to do so. Okay, so what kind of inequality can we create to get x squared by itself in the bottom there? Well, we know that x squared plus x is greater than or equal to x squared. Okay, because x in this case is greater than or equal to 1. Okay, so we can get rid of the x, but we need to include this inequality in that case. Okay, so we got rid of the x there. So then that means the left-hand side becomes bigger than the right-hand side. Okay, but we're not dealing with x squared plus x. We're dealing with 1 over x squared plus x. So in this case, we're going to have 1 over x squared plus x is less than or equal to 1 over x squared, which is a simpler looking upper bound. So this is an upper bound. Sorry. This is an upper bound. And it's simpler than what we started with. Okay, so it's much easier to work with this 1 over x squared instead. Now, by the comparison theorem, we know that if this upper bound converges, then this original function also converges. So by the comparison theorem, we know that if the integral from 1 to infinity of 1 over x squared dx converges, then the integral from 1 to infinity of the original also converges. Okay, so all we need to do is check this first part, and that will answer the second part. Okay, so let's do that. So we have the integral from 1 to infinity, 1 over x squared dx. Okay, the upper bound is infinity, so we've got ourselves an improper integral. So this becomes the limit as t goes to infinity, integral from 1 to t, 1 over x squared dx. So this becomes the limit as t goes to infinity, integral from 1 to t. We can write this as x to the minus 2. Okay, so this becomes the limit as t goes to infinity of minus 1 over x from 1 to t. So that will be the limit as t goes to infinity of minus 1 over t plus 1. Now, as t goes to infinity, this 1 over t is going to go to 0, so we're just left with 1. Now, we don't care what the value is, we only care that this is less than infinity. So, since this is less than infinity, the integral from 1 to infinity, 1 over x squared dx converges. And if that converges, then the original one also converges. Yeah, and that's what we care about. We wanted to show that our original one converges. Okay, any questions on this one? Okay, no questions. Okay, cool. So I think that's it for today. If you do have any questions later on, you can let me know through email or on the WhatsApp group. Okay, so all the homework solutions and all that for the improper integrals that's already been uploaded. So if you have any questions on the homework problems or the solutions are posted, please let me know. Okay. And if you have any questions about the other topics in the test, please let me know as well. So for Wednesday, that beginning part of the tutorial, that will be a normal tutorial session. So you can ask the tutors for any last minute help with regards to the test. And then from 10:30 onwards, we will have the usual test time. Okay, so 1 hour to write the test and then half an hour to check your work and submit. Okay. And then, sorry, one more thing for the catch-up test on the formative and the summative. Okay, that's coming up soon. I will post a list of those students that need to write those. Okay, so because of the late registration, they missed the first two. Okay, so I'll post the list again in case you forgot. And then the supplementary test, so class test 4, the list of students that qualify for that will also be posted, okay, as soon as I know. Okay, cool. But again, if you do have any questions before the test, please let me know or let the tutors know. Okay, bye everyone.